Hello everyone. Today we're going to be looking at this thing with density. Now, if you'll think back, we've talked about mass and we've talked about volume. Let's refresh for a second on those. Mass is how much matter is in an object. Remember that matter is the stuff that atoms are made of, so mass is how much stuff is in the atoms. If you look at these two, even though they're different sizes, they still have the same amount of mass. These atoms are the same size, and if we count up, there are a total of 9 atoms in both of them. So these two have the same mass. There's the same amount of stuff in there. The other thing we looked at is volume, how much space things take up. This box on the left takes up more space than this box. So even though the mass is the same, this one will have a larger volume. We can look at a different situation. Here, these two have the exact same amount of space. So they're going to have the same volume, but they have different masses. This one is going to have less mass than this one. If we put these two things together, mass and volume, we can talk about this thing we call density. And density is mass over volume. So to find the density, you take mass divided by volume. And really, this is a way of describing how crowded the space is. So for instance, if we look at these two, notice there's some space in between these atoms. Here it's really crowded together. That's one way of thinking of density. It's really just how much matter is packed into a given amount of space. And the more tightly that's packed, the greater the density. So if we go back and we're looking at this density equals mass times volume business, and again, density is how tightly packed in, how much stuff is in a given amount of space. Mass and volume, we know. We have some abbreviations that help us talk about density a little more quickly. The abbreviation for density is the Greek letter rho, that's spelled R-H-O. So this Greek letter rho that kind of looks a little bit like a P is the symbol we use for density. For mass, we use a lowercase m. It must be lowercase, that's important. And for volume, we use a capital V, always capitalized. So again, the abbreviation for density is rho. For mass, it's a lowercase m, and for volume, it's a capital V. So let's look at a type of number problem you might see for this. An object has a mass of 50 grams and a volume of 25 cubic centimeters. What is its density? So in order to do this, we'd use our equation. Density equals mass divided by volume. We know the mass of the object is 50 grams. The volume is 25 cubic centimeters. And now we divide this. 50 divided by 25 is 2. But whatever we do to the numbers, we have to do to the units as well. Grams divided by cubic centimeters is just written out as grams per cubic centimeter. So the density of this object is 2 grams per cubic centimeter. Okay, now we have a feel for what density is. It's how much matter is packed in a certain amount of space, and we know how to calculate it. Let's look at this thing in action. So what I'm going to bring up now is a program on the internet where we can just play around with what's called buoyancy. And the way it works is this. Whether or not an object floats in a fluid, like water, which is what we have here, well, not yet. Now we have water. So we have some water down here, and we have this object. And the thing that determines whether or not this object is going to float is actually the density of the object. Now here's the way it works. Water has a density of 1 kilogram per liter. So that is 1 kilogram of mass for every liter of volume. If an object has a density less than 1 kilogram per liter, it will float in water. If it has a density greater than 1, it will sink. So if we look at the density of this particular block that I've been playing with, its density is 0.4 kilograms per liter. It's less dense, there's less matter in a given amount of space in this than there is in the water, so it floats. I'm going to play around with the mass and change the density now, and watch how things change. As I increase the density, notice it floats less and less well. And as I get really close to 1, it just barely floats at all. As I get closer or farther and farther away from 1 in the lighter or less dense direction, notice that it floats higher and higher in the water. So an object with a density of 0.2 kilograms per liter floats very, very high. And we can change this so we can look at the density of different stuff. So here's wood. Ice, you can see, just barely floats in water. And now if I make this heavier, or not heavier, but rather more dense than water, notice it starts to sink. So at 1.02 kilograms per liter, it sinks in water. Now I'm going to bring it back up by making it less dense. Now I'm going to make it much more dense than water, and watch how quickly it sinks. As I crank up the density to 2 kilograms per liter, it just drops, well, like a stone. So I'm going to set this back now, and let's look at the weird case of what happens if it has the exact same density as water, 1 kilogram per liter. When the density is the same as the fluid, the object won't sink and it won't float. It stays right where you put it. So if I put this in the middle, it stays in the middle. If I put it at the top, it sinks down just below it and then stays right at the top. Just like that. Now, just so that you don't get the idea that this can only be done with water, we can change what this fluid is. Let's change it to, say, gasoline. Gasoline is less dense than water. It has a density of about 0.7 kilograms per liter. So now, whether or not this thing floats depends on whether it is greater or less density than 0.7. So at 0.66 it floats. Any higher than that, it's going to float higher. But as soon as you get over 0.7, it starts sinking. And this can go the other way as well. If we look at something that is much more dense than water, so let's go with honey at a density of about 1.42 or 3, somewhere in there. This thing will float right up until the density gets greater than that, at which point it starts sinking. The next thing we're going to look at is our first example of graphing in this class, and this is going to be a skill that you're going to be doing a lot of this, so let's make sure we get it down well now. So let's look at this graph, and the graph is of mass on the y-axis and volume on the x-axis. So as we go this way along the graph, our volume, the amount of space taken up, is increasing, and as we go up, the amount of mass is increasing. Now the thing we're going to be most interested in almost throughout the course is actually the slope of these graphs. And if you'll remember, slope is rise over run. So let's look at the slope of this line right here. The rise is going to be, if we look from here to here, between these 2 points, it rose a total of 25 grams. Now notice that grams. The y-axis measures mass in grams, so when we increase by 25 from here to here, we're actually increasing by 25 grams. Our run is how far we go on the x-axis, so we're going from here to here, so our run will actually be 5 cubic centimeters. So at 5 cubic centimeters, we can see now that setting up the slope of this is a division problem. So we can see this is 25 grams divided by 5 cubic centimeters. So our slope is 5 grams per cubic centimeter. But wait a minute, grams per cubic centimeter is a measure of density. The slope of this graph will actually tell you the density of the object. And that's not all we can use this graph for. Suppose, for instance, you want to know if you have 25 cubic centimeters of this material. So you have whatever this is, and its volume is 25 cubic centimeters, and you want to know how much mass that will have. If we go over to 25 cubic centimeters, we follow that up the graph, and then go over, we can see that 25 cubic centimeters will have a mass of 125 grams. And notice we can do this for anywhere on that graph. But now here's a question. What if we want to know how much mass will be in 50 cubic centimeters of this material? Well, we go out to 50 and we follow it up, but notice our graph doesn't get all the way there. So we have no way to tell for sure how much that is. Now, obviously you could draw the graph out there and then measure it. There's nothing wrong with that. But say we wanted something that's even off our graph, 100 cubic centimeters, 1,000 cubic centimeters, something like that. There is a way to do this. All we have to do is come up with the equation of this line. So in order to do that, we're going to use what's called slope-intercept form and actually write out the equation for this. So slope-intercept form is y equals mx plus b. And let's just go through this piece by piece and see what all these mean. Y is the measurement on the y-axis. Well, we know what the y-axis is measuring. It's measuring mass. So we can just replace that y with mass. M represents the slope. Well, we've already calculated the slope of this. The slope is 5. X, on this graph, x represents the volume, because that's what we're measuring along the x-axis. So our equation has now become mass equals 5 times volume plus, and now there's the b out here. What does that mean? The b is the y-intercept, so that's the place where this line crosses the y-axis. And if we can extend that out, imagine drawing this line, you could see that it crosses the y-axis at 0. Now that's on the y-axis value that we're looking for, because we know x is going to be 0 at that point. So we want to know what its value on the y-axis would be. Here it's going to be 0, and in fact, of almost all cases, no, not almost all cases of mass versus volume, it's going to be 0. But in general, whatever equation you're using, this number describes the y value when the line crosses the y-axis. And so here it's going to be 0. When we get rid of that, because plus 0 doesn't change anything, the equation for this line becomes mass equals 5 times the volume. So now I can find the mass for whatever volume I want. If I want to know the mass when the volume equals 100 cubic centimeters, instead of writing volume there, I would just plug in the number 100. 100 times 5, the mass would be 500 grams. This works the other way too. If I want to know what the volume will be when the mass is, say, 50 grams, we can check that on here. We know it should be 10. If 50 equals 5 times something, we divide by 5, and the volume there would be 10 cubic centimeters. So now I can use this equation to figure out any mass or volume for this substance that I may need.